Welcome to Brain Vision.
So here in this problem we are given this room with dimension 4 meter cross 5 meter cross 6 meter. This is basically the volume of the room, and heat is being lost from the room at the rate of 150 kilojoule per minute, and the initial temperature of the room is 15 degrees Celsius, and the local atmospheric pressure in the room we have 98 kilopascal. Now this section is our duct, and the power rating of the fan we are given as 200 watt, and the average mass flow rate in the duct we have 40 kg per minute, and the time taken to increase the room of the temperature from 15 degrees Celsius to 25 degrees Celsius, delta T we are given as 25 minutes. Now there are two parts in the equation. In the A part, we have to calculate the power rating of the electric heater. Power rating means basically the rate of work done by the electric heater. So we'll be solving the A part first. Now to solve this problem, we'll be calculating the mass of air in the room. So M, by using the ideal gas equation, we can write this thing as PV over RT. And we are taking in the initial condition, so P1 and this is T1. Now pressure is given as 98 kilopascal, so we can plug it here. This is 98 kilopascal, and the volume we have this much, which would be equals to 120 meter cube, divided by R, which is constant and its value is 0.287 kilopascal meter cube over kg Kelvin, times temperature T1 is 15 degrees Celsius. Initial temperature was 15 degrees Celsius, and in Kelvin it would be 288 Kelvin. So from here we'll get the mass of air inside the room will be 142.3 kg. Now next we'll be considering entire room as our system. That means I'm taking this whole as our system, and we'll be applying the energy of conservation of energy, or the first law of thermodynamics in this system. So we can write that energy in minus energy out is equals to change in energy of the system. So energy in, we have the rate of work input by the electric heater, so work input by electric heater plus the rate of work input by the fan. Now next, heat is being lost, so minus Q out is equals to, now there is no change in potential energy and the kinetic energy of the system, so it would be equals to change in internal energy of the system. So from here we can write delta U as M CV T2 minus T1 over delta T, and it would be equal to same thing, so work input by electric heater plus work input by the fan minus heat out. Now from here we're going to simplify it for the work input for the electric heater. Now from here the expression for work input for electric heater would be equals to, we can take these two terms towards the right side, so it becomes Q out minus the rate of work input by the fan plus MCV T2 minus T1 divided by delta T, and delta T we have 25 minutes, so delta T as it is. Now we can put the values. So Q out we have 150 kilojoule per minute, but we'll be converting into kilojoule per second. For that I'm dividing it with 60, so this much of kilojoule per second minus the rate of work input by the fan. So we have 200 watt, but we'll be taking into kilowatt, so it would be equals to 0.2 kilowatt plus mass. So mass of air we have calculated as 142.3 kg times CV. CV for air we know it is 0.718 kilojoule over kg Kelvin times T2 minus T1. So T2 minus T1 would be 25 degrees Celsius minus 15 degrees Celsius, that is 10 degrees Celsius, and divide by delta T. Now delta T we have this much, so we can change the units into second. It is in 25 minutes, means multiplied with 60, so this much of seconds. Now we're going to simplify this and we'll get the rate of work input or the power rating of electric heater as 3.151 kilowatt. So this is the answer for the A part. Now next we'll be solving the B part. Now in the B part, we have to tell the temperature rise that the air experiences each time as it passes through the heater. So for that we'll be considering this as our system. That is the duct we are assuming to be our system. Now here also we'll be applying the energy balance equation on the duct. So we have energy in, this is the rate of energy in minus rate of energy out, is equals to change in energy of the system. Now this system is a control volume and there is no change in internal energy of the system because the rate of change in internal energy plus the rate of change in kinetic and potential energy of the system is 0. So delta E of the system would be 0. Now energy in, we have the rate of work input by the electric heater plus the rate of work input by the fan and plus the initial enthalpy, that would be m dot h1, and it would be equals to minus energy out, we have m dot h2 and it would be equals to 0. Now from here we can take these two terms towards the right side, so we can write the work input by the electric heater plus the work input by the fan, and it would be equals to m dot h2 minus m dot h1. Now this would be equals to m dot Cp T2 minus T1, and this would be as it is, so work input by the electric heater plus the work input by the fan. Now we have to calculate this delta T, so we can take these two terms towards the left side, or we can write T2 minus T1 would be equals to the work input by the electric heater plus the work input by the fan divided by m dot Cp. Now we have all the values, we can plug it here to calculate delta T. So T2 minus T1 as it is, that we have to calculate, is equals to the work input by the electric heater that we have calculated as 3.151 kilowatt plus the work input by the fan we have 200 watts, that means 0.2 kilowatt divided by m dot. Now m dot we have given in the equation as 40 kg per minute, but we'll be converting it into kg per second, so I'm dividing it with 60. So this much of kg per second times Cp. Now Cp for the air, it is for air we know it is 1.005 kilojoule over kg Kelvin. So from here we'll get the answer as nearly 5 degrees Celsius. So we can conclude that the temperature rise that the air experiences each time it passes through the heater would be 5 degrees Celsius. So I hope you have understood the problem. Thank you.